Well, hello everyone, and welcome to this first lecture in the first year lecture series for materials science and engineering. Now, we'll study a number of things as we progress throughout this course. We will study material properties, and I want to develop a solid understanding as we go throughout the course of relating material properties to their atomic structure. And of course, if we're going to learn something about how the atomic structure, particularly the crystal lattice of solid materials, affects the physical properties of a material and how it behaves when it's put to work, as it were, we need to have an understanding of atomic structure. So today in this lecture, I just want to go over some aspects of atomic structure. I want you to gain a qualitative understanding of basic atomic structure. I'd like us to be able to describe some of the important quantum mechanical principles relating to electron energies, and I also want us by the end of this session to be able to describe ionic, covalent, metallic bonds, and also some of the hydrogen and van der Waals forces that allow atoms to interact and bond. So some fundamental concepts then, and I know that this many of you will have GCSE science, many of you will have A levels possibly in physics and chemistry. So for some this may be a recap. If this is new to you, then I would direct you to the directed reading for this lecture, and please take a look at the supplementary YouTube videos that I supply also. But fundamentally then, atoms consist of a very small nucleus, which is composed of protons and neutrons, and these are broadly encircled by moving electrons. So the electrons and the protons are the electrically charged subatomic particles here, and they have a charge of 1.062 times 10 to the minus 19 coulombs. Neutrons are electrically neutral, and they sit, as I said, in that nucleus. All of these subatomic particles have very, very small masses. So a proton and a neutron have a mass of about 1.67 times 10 to the minus 27 kilograms. An electron is even smaller, with a mass of about 9 times 10 to the minus 31 kilograms. And that's a good start for any model of the atom then. A cluster of protons and neutrons in the middle, encircled by moving electrons. And we characterize an element within the periodic table by its number of protons. So you can see that hydrogen there has 1 proton. Of course, a complete description of an atom needs a little bit more. So we may wish to describe a relative atomic mass, for example, or we may wish to describe its symbol. A whole atom then has, if you like, a complete atom has the same number of electrons and protons, and the atomic mass is the sum of masses of protons and neutrons in the nucleus. The number of protons is the same for all atoms of a given element, but the number of neutrons can vary, and we call these isotopes. We just said that the atomic mass of an atom is its mass of protons plus neutrons. So if we remove a neutron to create a different isotope of an element, then we're going to affect its atomic mass. So have a look at the natural isotopes of carbon there. There's carbon 12, 13 and 14. You'll note that they all have exactly the same number of protons, but it's the number of neutrons that differs here, carbon 13 and 14 having 1 and 2 extra neutrons respectively. And you see that the natural abundance of carbon-14 is 1 part per trillion. Okay, so really not doesn't naturally occur at all, but the natural abundance of carbon-13 is about 1.109%. And of course, this is what makes it possible to radiocarbon date a lot of ancient artifacts that are found in the ground. And you'll note then that the atomic weight that is found on the periodic table for carbon is an average weight of all of the atoms naturally occurring isotopes. And you'll note that's a weighted average, so it's done by relative abundance. Okay, so what kind of atomic models have we been through then over the years of development? Well, in the 19th century, scientists drew the conclusion that electrons couldn't be explained by classical mechanics. So Newton had all these wonderful mathematical equations that described the movement of the planets and described the movement of large objects. But such classical mechanics was inadequate when it came to describing the behavior of such tiny subatomic particles like the electron. And so the field of quantum mechanics was born, and a very early player in that field was Niels Bohr, and you can see his picture in the top right there. And the models went through lots of different variants, right? So you can think right back to things like the plum pudding model, which you may have learned about at GCSE. I'm going to start with Niels Bohr model, which assumes that electrons revolve around the nucleus in discrete orbitals. And I have represented these orbitals as circles in the picture that you see there. And the position of that electron is defined by its orbit. Now, this is a crude model of the atom, but is okay for now. Now, one important point of this atomic model is that electrons are quantized. So they can have, or are permitted to have, only very specific values in energy. And they can, of course, change that energy. They can undergo a quantum jump. They can move from one energy level or orbit to the other. And they do that by absorbing and emitting energy. So you can view these as energy levels or states that are separated by finite energy. Now, the Bohr atom had significant limitations, and it was resolved by the update to the model, if you like, which was the wave mechanical model, which is where we now treat an electron as both wave-like and particle-like. It has properties of both. And instead of saying that these electrons are definitely within these finite orbits, we describe an electron by a probability function. So a probability of being at a particular location around the nucleus. So the position of the electron is now described by a distribution of probability, or what we would call an electron cloud, or which is perhaps now commonly known as an atomic orbital. And we can compare that approach with the Bohr model because it's useful to compare the development of models. So the Bohr model would have had nuclei at a fixed finite energy level, whereas the wave-particle duality model has it as a probability distribution. And you can see in the image there the two distinctly different approaches on the left-hand side in red, which is the Bohr model, and the right-hand side in green, which is the wave-particle duality model. Now, this is a really important point because both of these models tend to be used in material science. And some of you watching this may be physicists, some of you may be electronic engineers, some of you may be mechanical engineers. The important point here is that you use whichever fits the system under investigation. My advice when considering these things is to keep it simple if you can. So if you need a simple model of electron transitions in a material, for example, you're probably going to use the Bohr model because it's much more simple. Okay, so moving on and considering the wave particle model then. When we speak about this kind of wave mechanics, every single electron can be characterized by 4 quantum numbers. And we can think of these quantum numbers as a bit like an address. Each quantum number gives us a little bit more information and helps us identify where an electron might reside. The size, shape, and spatial orientation is defined by 3 of these quantum numbers. Shells are specified by the principal quantum number n, and that's written as 1, 2, 3, or 4. Sometimes in material science you might see it written as K, L, M, and N. This usually means that you're conducting some kind of spectroscopic experiment, such as X-ray photoelectron spectroscopy. But this number is related to the size of the electron's orbital and its average distance from the nucleus. So the subshell then is designated by the azimuthal quantum number, or L, and this can take on integer values from L equals 0 to L equals n minus 1. Each subshell is denoted by a lowercase letter S, P, D, or F. And this really describes the shape of the orbital. So the principal quantum number tells us how far the orbital is away from the nucleus. The azimuthal quantum number tells us the shape of the orbital. And you can see there, that in that image on the right, the red orbital at the top is an S orbital. The orange orbitals are P orbitals. The blue orbitals are D orbitals, and the green are F orbitals. And you can see there are lots of different shapes, and these are essentially probability clouds, if you like, that are derived from the mathematics. Now, if we've got subshells, then you'll note, for example, the S subshell only has 1 orbital. But you'll note that the P orbital has 3. The P subshell has 3 orbitals. If you look back to the previous slide, the D subshell has 5 orbitals and the F subshell has 7 orbitals. So we need a way of differentiating the atomic orbitals within any given subshell. So the number of electron orbitals in a subshell is determined by what we call the magnetic quantum number. And this can take on integer values between minus L and plus 11, and that can include 0. So for example, when L equals 0, ML equals 0, and that describes the S subshell with its 1s orbital. When L equals 1, we're talking about a P subshell here, ML can equal minus 1, 0, and 1, and that makes sense because there are 3 orbitals in the P subshell. Importantly then, all of the orbitals within a given subshell have an identical energy. And finally, if we're going to pin down that electron even further, if we're really going to work out its address, then we need to describe it using the 4th quantum number. And associated with every single electron is a spin moment, and that can be described by the ms quantum number. So it can be, an electron can have its spin oriented as spin up plus a half, or spin down minus a half. And you can see that in the image on the right there. And what this tells us, what it demonstrates, is that every single orbital within a given subshell can accommodate 2 electrons. So in terms of working out electron configurations, well, we need to determine the manner in which these states are filled with electrons. So we've just described the address of an electron, if you like. We've said how to pinpoint it. And we know there are distinct energy levels as you move away from the center of the atom, from the nucleus. But how do electrons fill these systems? Well, you can use the Pauli exclusion principle. And there's a picture of Pauli in the top right there. And this essentially states that that you can have two electrons in each state, and they must have opposite spins. So what we're saying there is that you can have two electrons in each atomic orbital, but they must have opposite spins, i.e. plus a half or minus a half. So an S, P, D and F subshell can accommodate 2, 6, 10 and 14 electrons respectively. And you'll see there I write an electron configuration in the bottom right of the screen, 1s1. Well, the big one in blue there is the principal quantum number. It tells us the energy level we're at with respect to the nucleus, if you like. It tells us how far we are away from the nucleus. The S in pink there is our orbital angular momentum quantum number. That tells us which subshell we're in, and the one in green tells us the number of electrons in that subshell. And electrons fill up from the lowest state first. So they'll start closest to the nucleus and they'll fill moving away from it. The electron configuration that you see in the periodic table then is the ground state electron configuration. This is before the atom's reacted with anything or before it's been ionized. So you can see there the ground state electron configuration for the first 5 elements in the periodic table. Now, valence electrons are the electrons that occupy the outermost shell of an atom. And these are really, really important electrons because they're the ones that participate in bonding. So, dependent on how the outermost shell is filled in an atom, we may expect to find very different reactivity. So what we find is that many physical and chemical properties of solids are based on these outer electrons. So for example, if you look at the right-hand side, far right-hand side of the periodic table, and you have a look at the noble gases, you may expect, because they have a closed configuration in their outer shell, they have the maximum number of electrons that you can get in the outer shell, you may expect, and you would be right, that they are very unreactive. They don't like to react with anything. Conversely, if you move over to the far left-hand side of the periodic table and you look at the group 1 metals, something like sodium or lithium, you know these are highly reactive. I'm sure you've seen the YouTube videos or you've done it in school. You drop sodium into a bath of water and it almost explosively reacts because it has just 1 electron in its outer shell and it wants to get rid of that so that it can leave the next shell full and it can become much more stable. So dependent on how this outer shell is filled, ultimately dictates the properties of the element or compound in question. And this has very important ramifications when we're talking about large assemblies of atoms, so crystalline solid materials, which will form the basis of this module. And I think this just reiterates what I've said here. Some atoms have very stable electron configurations, and here are the noble gases: helium, neon, argon, krypton and xenon. They're all happy, they've got complete outer shells. Okay, so we've got a load of elements. We know there are lots of different types of elements. And how do we classify them? Well, we put them all into a periodic table. And just to reiterate here, again, I'm sure lots of you have studied the periodic table whether that be in GCSE science or A-level science. But moving from left to right, we've got increase in atomic number, and they are arranged into horizontal rows called periods. And these are arranged in such a way that elements in each column have similar valence electron structures. Essentially, they have the same number of electrons in their outer shell, although as you move down the group, that outer shell becomes further and further away from the nucleus. So what that does is it causes the properties of an element in any group to change as you move down or across the periodic table. So think about, if I go back to, again, the group 1 metals, lithium through to francium, you may not remember Brainiac as children, but I used to watch a show called Brainiac as a child, and they used to do crazy things like lob huge chunks of sodium into baths and see what happened. And I always remember that when they threw lithium and sodium into a bath, it reacted very explosively, but it was nothing in comparison to throwing cesium into a bath. And that's because the outermost electron in cesium is much further away from the nucleus. So it's shielded from the nucleus. It's less gripped by the nucleus, if you like, and cesium's much more willing to give up its electron than the smaller elements in that group, like lithium or sodium. And of course, it reacts with much more explosive tendency. So that gives you an idea of how the properties of any element in a group or groups of elements change as you move down that group. So as I said, the group and this is an important point actually, the group that the element is in shows the number of valence electrons. So we've got there the inert gases or the noble gases, and they are found in group 8 of the periodic table, and they have 8 valence electrons. And conversely, if we move over to the other left-hand side of the periodic table and look at group 1, so hydrogen through to francium, these have just 1 valence electron. And similarly, the group in the middle, so on this particular notation, group 3b through to group 2b, are called the transition metals. And they're called so because they have partially filled d orbitals. And because they have partially filled d orbitals, they show some very interesting properties, both in solution but also in the solid state, because those electrons can very freely move around those d orbitals and be promoted and recruited back down from various energy levels. And all of these elements alloy very well with other elements in the periodic table. So you've got to think of things like iron and its importance in steel. A lot of these elements then are going to form very important bases for our discussion surrounding alloy materials. And that will be much later on in the course. Now, if you look at, again, this notation here, group 3A through to group 5A, or group 3 through to group 5, these elements show characteristics that are intermediate between metals and non-metals. And again, that's a function of their electron configurations. Now, most of the elements in the periodic table are indeed metals. And metals are very electropositive elements. They are willing to give up electrons to become positive ions. And these are on the left-hand side of the periodic table. If we look at elements on the right-hand side of the periodic table, then they are very electronegative, and they like to accept electrons, forming negatively charged ions. So in fact, if you look at the image there, fluorine is the most electronegative element in the periodic table, very closely followed by oxygen. So you can see that the elements on the left, in blue are very electropositive, whereas elements on the right in sort of green, yellow, purple, and red are very in yellow, purple, and red are very electronegative. Okay, so I want to now develop an understanding or begin a discussion surrounding atomic bonding in solids and the types of atomic bonds that we see in solids. And I don't want to get too complicated here. So a lot of the more simple models of bonding that you may be familiar with from things like GCSE and A-level actually hold far into some of the depths of theoretical material science. Excuse me. And we want to learn about bonding because we later on in the course we're going to want to know how and why materials are held together. But a lot of the time we can start to relate the properties of a material from knowledge of those interatomic forces that bind atoms together. We may look at a type of material that's composed of two elements and think or predict the kind of bonding present and be able to make some inferences about the strength of that material, whether it will fracture under tension or whether it will be a ductile material. And that's because often when we fracture a material or a material fails, those atomic bonds are broken. So if we know something about the interatomic forces that bind atoms together within a material, then we can make inferences about its properties. Okay, so before we do that, let's have a chat about bonding forces and energies. Let's first consider how two completely isolated atoms interact as they are brought closer together from an infinite separation. So imagine that you have an atom in your left hand and an atom in your right hand and put them out either side of your body and slowly bring them together. And take a look at that graph, which is a plot of the force and interatomic separation. So below we've got repulsion and above we have attraction. So at very large distances then, I'm starting on the far right hand side of my graph there, as I bring my hands or my atoms together, they are separated by relatively large differences and interactions are pretty negligible. They don't even know each other are there really. As I start to bring my hands or my atoms much closer together, suddenly they start to realize each other. And at much smaller separations, atoms start to exert a force on each other. And the attractive force and the repulsive force depend on the radius of the atom in question. Attractive forces then will depend also on the type of bonding present. Repulsive forces are interactions between negatively charged electron clouds. So we've got lots of things going on here. We've got two atoms that perhaps want to bond, so there is an attractive force present. But we've also got two atoms that have, probably, if we're talking about metals, quite large electron clouds. So as you bring those together, there's going to be a little bit of electrostatic repulsive forces. Now, if we think about the net force between those two atoms, if we sum the attractive and the repulsive forces, and you can see that is shown in red there, that then is a function of interatomic distance. And when that attractive force and that repulsive force are equal, there is no net force, and hence a state of equilibrium exists. Now, I showed you that in terms of an attractive and repulsive force, but it's much more convenient to work in terms of potential energy. So again, if I plot attractive, repulsive, and net potential energies on exactly the same graph, the minimum in that net energy curve is the equilibrium spacing, or is the point at which two atoms will bond. And that's the energy that is required for a bond to form. The energy at this minimum point is now the energy that's required to yank those two atoms apart. And this bonding energy, if you like, the strength of this bond, how much energy is required to rip these two atoms apart, will vary dependent on the types of atoms that are present. So therefore, it's very different for different materials. Some materials are much easier to snap than others. And of course, that depends on the type of atomic bonding that's present. So you see then for that bonding energy, E0 if you like, materials with a very large E0 tend to have high melting points. They tend to be solid substances. They're difficult to break or melt. And materials with a very small bonding energy then tend to lie in the gaseous state. And those that have intermediate bonding energies, the liquid state tends to prevail. Okay, so I would like to now spend the last little bit of this lecture talking about the three different types of primary or chemical bond present in materials. And of course, those are ionic, covalent, and metallic bonds. And each type of bond here involves those valence electrons. So the types of bonding that you see here arise when atoms try to assume that stable electron configuration or an octet. Okay, so again, I'm going to keep the descriptions of bonds here fairly simple. There's no need to develop these into more complex models of bonding, because a lot of them hold for some of the concepts that we're going to be discussing as the module progresses. The first one is an ionic bond, and it is found in compounds composed of metallic and non-metallic elements. So sodium chloride is a good example here. And what happens in this kind of bond is that the metallic element gives up their valence electrons to the non-metallic element. So you see here sodium, which is desperate to lose its outer shell electron there in yellow, gives an electron to chlorine, which has 7 electrons in its outer shell, but with the donation from sodium, it now completes its outer shell and has 8 electrons. So both of those elements there are now happy and satisfied. Now, in the process then, chlorine obtains a net negative charge and sodium obtains a net positive charge, but both of these atoms now have a stable outer shell. And because of that difference in charge then, that ultimately is what holds this solid together. So there are attractive forces in such a bond. They're Coulombic or electrostatic in nature. And the bonding here is non-directional. So the magnitude of that bond is equal in all directions. And for an ionic material to be stable, you think about a teaspoon of table salt, that's a stable material, it's sodium chloride. All positive ions must be surrounded by negatively charged nearest neighbours. And we'll see as we start to discuss the structure of these materials in terms of the crystal lattice, we will see that this holds. So what about a covalent bond then? Well, these bonds tend to form when the atoms in these materials have very small differences in electronegativity. So think about the previous case with an ionic bond. We were talking about sodium and chlorine. Well, sodium and chlorine have very, very high differences in electronegativity. Chlorine is a very electronegative element, whilst sodium is a very electropositive element. But this covalent bonds tend to happen when you've got atoms with very small differences in electronegativity. And instead of one atom donating an electron to the other, a stable bond here occurs when electrons share. And each atom must contribute at least one electron to that bond. So think about molecular hydrogen, H2. This happens when two hydrogen atoms come together and each one donates one of their 1s valence electrons. In the process, by sharing atoms, each atom acquires a stable outer shell. And what happens here is that electron orbitals actually overlap. And you can really, if you like, read into this and develop this as a highly complex model. It's called molecular orbital theory. And essentially those atomic orbitals overlap, but because there is a specific overlap between two or more atomic orbitals, that bond now has a directional component, very specifically between two atoms. And the bond exists only in the direction between those two atoms, and we would call that direction the internuclear axis. The final type of bonding that I want to talk about is metallic bonding. And clearly this is found in metals and their alloys. And what happens in metallic bonding is that valence electrons form a sea of electrons, or a sea of negative charge. Those electrons come from metals that have lost an electron. Remember, metals are nice and electropositive and they want to lose an electron. Those remaining atomic nuclei, the metals and any non-valence electrons, form ion cores then, or islands of net positive charge. And those free electrons shield ion cores from repulsive interactions. And if you like, they act as a glue that holds the material together. And unlike the covalent bond, but like the ionic bond, the bonding here is non-directional in manner. There are a couple of other bonds or types of bonding that I want to talk about. And these bonds, whilst they involve electrons, they don't involve the loss or exchange or sharing of electrons. They involve, if you like, the movement of electrons within an atom. So we can talk about these, and we define them as secondary or van der Waals bonding, and they're very weak in comparison to the primary atomic bonds that we've spoken about, ionic, covalent, and metallic, but they can be very important in materials science and engineering. And they arise from atomic or molecular dipoles, and this is a really important point. We're not necessarily just talking about bonding between atoms now. We could be talking about bonding between molecules. We can define an electric dipole as when there is some kind of separation and positive and negative portions of an atom or molecule. And bonding results then by Coulombic attraction between positive and negative ends of these dipoles. So take a look at the image on the bottom there. Let's imagine that was two atoms, and something had forced all of the electrons over to one side of the atom, and all of and therefore leaving a positive charge on the left-hand side of the atom. Well, you might expect then that there would be some kind of interaction. If this happened over a very large assembly of atoms, because they now have difference in charge on either side of the atom, you might expect them to rearrange themselves and interact through these kind of secondary or van der Waals bonds. And you can get a couple of different cases here. The first is a fluctuating induced dipole bonds. So atoms are constantly in motion. They are under constant, even in a solid, they're under constant vibrational motion. And this constant vibrational motion can cause very short-lived distortions in electrical symmetry. So again, you might have a case where over a very brief period of time, you have a higher concentration of electrons on one side of the atom than on the other. And that creates very small electric dipoles. If you've got one dipole, if you have a concentration of electrons on one side of an atom, then it might induce a dipole in a neighbouring atom. And if it does, then they will be weakly attracted to each other. Now, when you've got assemblies of billions and billions of atoms, this can have quite a distinct effect on the arrangement of atoms and also the way in which atoms interact with one another. Now, these attractive forces, these induced dipoles, are only temporary, and they fluctuate very, very dynamically over time. And that, again, as I said, they tend to operate over very, very large numbers of atoms and molecules. So we find these kinds of interactions in materials with quite low melting points and boiling points, so primarily gases. And they are, in fact, the weakest intermolecular bond. We can also have polar molecule-induced dipole bonds. So again, I'm talking about molecules here, not atoms. A good example of this kind of molecule is HCl, or hydrochloric acid. And it happens in molecules where a permanent dipole moment exists. So in some molecules, because there is an asymmetrical arrangement of positive and negative charged regions, it causes polarity. So look at hydrochloric acid here. There is a permanent dipole in that molecule with a net positive charge that's associated with the hydrogen atom and a net negative charge associated with the chlorine atoms. Now, that molecule having such asymmetric charge distribution can induce a dipole in another neutral molecule, and bonds will form as a result of attractive forces between these two molecules. Now, if you can have induced dipoles, then you can also have permanent dipole bonds, and Coulombic forces can exist between polar molecules that are next to each other. And this is the strongest type of secondary bonding. And it's normally called hydrogen bonding, and it occurs between molecules where hydrogen is covalently bonded to a very electronegative element, such as fluorine or oxygen. And a good example of where this occurs is in hydrofluoric acid. Okay, so I will stop there. I will go over with some of the I'll go over some of the key points of this lecture. We've learned that the electron has both wave-like and particle-like properties and can be characterized by 4 quantum numbers. And the electrons fill up from the lowest energy state first, and no one electron can have the same 4 quantum numbers. We've discussed how elements are arranged in the periodic table, and they are arranged according to their electron configuration. We've looked at the 3 types of primary interatomic bond, ionic, covalent, and metallic, and we've taken a look at some of the secondary bonding that can exist between atoms and molecules.